Hey everyone. In this video, I'm going to go through a coding example to show you how to replicate one of the plots in our textbook, specifically on the coverage probability of confidence intervals. What is meant by the coverage probability is specifically how often a certain confidence interval over repeated sampling generations or repeated data generating processes will in fact contain the true value. Okay, so usually for 95% confidence interval, we would expect that confidence interval will include the true value 95% of the time. And so we will go through some code to simulate some data generating process and show this behavior for 95% and 50% confidence interval the same way it has been done in the graphic in, I believe it was chapter 4, in our textbook reading for this week. Okay. I will, however, simulate slightly different data. What I'm going to look at here is we will directly look at the sampling distribution for and the confidence interval around a regression coefficient based on one of the simulation scenarios that is also in the book earlier on. I believe it was in the first chapter when the authors kind of show the regression framework based on simulated data to estimate treatment effects. Okay, and so we will use the same framework, the same kind of data generating process, and we will generate multiple data sets and analyze each data set in kind of a loop, and then plot the confidence interval for 100 repeated data generating processes. Okay, so the first thing we're going to do here is we have to simulate data from our linear model. Okay, first we're setting a seed. This is just some number. This is just an example. This is the zip code where I grew up in Germany, but you could use any other number. This is just to make the results replicable, right? So if you put in the same number and you generate random data, you will get exactly the same data with that seed. If you don't include a seed, then it's going to be a new set of random numbers every time you execute that code. Okay, so if you want to get exactly the same results, use the same seed. If you want slightly different results, or if you want different results every time you run the code, just remove this command. Okay, what we're going to do is we're going to simulate first a population, and our population here is just of size 1000, which is of course smaller than usual, for example in the context of survey research, smaller than the usual populations that we're dealing with, but this is sufficient for our purposes. The way we simulate our population is we just create a tibble. We have an ID for each individual, for each observation in that population that just goes from 1 through 1000. Then we have one independent, continuous independent variable, which is just a random draw from a uniform distribution of size 1000, of course, that ranges between 1 and 5. And then we have our dependent variable y, which is again a random draw here now from a normal distribution. Again, 1000 draws, but the key here is that the average of that normal distribution is conditional on x. So the kind of systematic component here is 10 plus 3 times x. You could think of this as this will ultimately be kind of the regression equation that we will want to estimate, and the standard deviation is 3. So that's kind of the, you could think of this as the error term. Okay, so every y is a random draw from a normal distribution with standard deviation 3, and the average of that normal distribution is basically determined by this formula. Okay, so that sets up our population, and we can think of this population as, we can't observe the entire population, but what we can do is we can take individual samples from that population. In our case now, perfectly random samples. Okay, so what we're going to do is we're going to write a loop to take 100 samples of size 50. So we take, we kind of, in the hypothetical world, where we could repeat our sampling procedure 100 times. Each time we collect, take 500 random respondents and include them in our sample. Okay, and this is what we're going to do. First, we declare the sample size, so the number of observations in each sample. And then we create a list, which will just be a container to save basically the resulting kind of sample that we collected. Okay, and of course there are more efficient ways to do this. We wouldn't have to save them all separately in a list, but this way we kind of directly see each data set and we can kind of treat them as separate samples. Okay, so this is going to be a list of length 100 because it's going to contain 100 separate data sets, 100 separate samples. Okay, and then we'll create a loop that ranges from 1 through 100, and in each iteration it will basically save in the ith element of that list that we created earlier, df underscore samp. We will just sample a subset from our population. So we take our df underscore pop, so the population data frame, and we only select a few. Specifically, we select 500 random 50 random observations from that 1000 observation tibble, and then save this in our df underscore samp list. Okay, just to make things easier, I also arrange the observations by ID, just so we have the IDs again kind of in ascending order. Okay, so how does one individual data set constructed like this look like? dfsamp, now this is a list, and we use 2 brackets to select elements from a list. So the first kind of sample that we collected from this population that we generated using simulation is just a 50 by 3 tibble. We see our independent variable, we see our dependent variable, and we see here the ID. So now we know, okay, in sample 1, we randomly selected person 81, observation 82, observation 92, and so on. Of course, 50 observations total, right? dfsamp, of course, is a list, and it contains 100 such samples of size 50, okay? So now we already have our repeated 100 samples. The next thing we have to do is we have to run a regression and plot that regression. And so the first thing I'm going to do is I'm just going to kind of replicate the initial regression plot that you already saw in the textbook, where we talked about continuous predictors in the context of the simulated kind of experimental data. And the way we can just plot the regression line and the actual scatter plot for one sample is we just select one element from our list of samples. Of course, our aesthetic mapping is x and y for the specific x and y axis. We add our scatter plot as well as a linear fit, and then add some labels consistent with the plot that we want to replicate in the textbook. Okay. Then so the result of this plot is actually already here. This is what we're going to see. The slope of this regression line, of course, is approximately 3, and so with every 1 unit increase in the treatment indicator, we observe an average increase in the outcome measurement of 3 points on the scale of the outcome measure. Okay. We can, this is basically directly using the geom_smooth command. We can also directly run a linear regression using LM. And as we talked about in the past, LM is kind of the base R command to run a regression. Later on, we will use a different function stan underscore GLM, which ultimately will give us similar results, but has some other capabilities. But for now, we'll just use the linear regression command that you already know from last semester. Okay, so we can save this linear regression based on the first sample that we collected. And then I just clean the output of this regression model using the tidy command from the Broom package, which directly gives us a little overview of the regression coefficients, intercept and slope coefficient, standard error, t statistic, and the corresponding p-value. Okay, so this is just to kind of visualize the coefficients that were estimated to fit that line. Okay, the next thing we want to do is we want to write a function to extract the confidence intervals across all these 100 samples, right? So essentially, we don't want to do manually construct the confidence intervals for 100 samples. That would be a lot of typing or a lot of calculation. So we want to do that automatically, and in order to do that, we'll just write a quick custom function. Okay, I will. The first thing I'm doing here is I'm loading the Broom package because I want to use the tidy command or tidylm command, as well as the confint underscore tidy command to extract this information from our regression model. And so our function, our custom function that I'm defining here is just called extract confint. This is a function that has just one input, which I call x. And this x will directly be inserted in this tidy command, which we already kind of saw. Right. Oops. Now I'm getting. Sorry. Which I already kind of demonstrated here. Where you see, okay, tidy kind of takes the regression output and converts it into a tibble containing estimate, standard error, and so on. By including this option conf.int equals true, that means we directly include the confidence intervals for the 95% level as well. Then I just rename those two columns that contain the confidence intervals, and then I add additional confidence intervals for the 50% confidence intervals, because we want to compare both the 50%, the coverage of the 50% confidence interval, and the coverage of the 95% confidence interval. Then I rename those accordingly as well, and the resulting tibble now of this extract confint function, if we kind of use this just with our M1, which is just the first model based on the first sample that we took, is a 2x9 tibble with, again, our estimate, standard error, and so on, including two confidence intervals, one for the 95% level and one for the 50% level. Okay. So that's nice. Now the next thing we want to do is we want to basically run this function for all 100 samples. So we want to extract the confidence intervals across 100 separate samples. The way we can do this is we take our df underscore samp, which, remember, is a list of data frames, a list of length 100 with each element being one 50 by 3 data frame, essentially. In order to kind of apply the same function for each element of that list, we could write a loop manually, the way similar to the previous loop that I showed you. But loops in general in R are computationally not very efficient. So the way we want to do this is we want to use the map function. The map function essentially does the same thing as a loop. It takes, in this case, the list as an element, and then applies the same procedure, the same function to each element of that list, okay? And the function that we want to apply here is just the linear regression with y being the dependent variable, x being the independent variable, and the data, where we have this little dot here, is basically now each element in our df_samp list, okay? So this map command basically allows us to, in a more computationally efficient way, and easier, like more simple way, to directly repeat this command for each element of that list. Okay, so we basically run 100 regressions with just one line of code. So that's pretty nice. Then, of course, we want to further, we don't want to just use this regression model, but we want to use our extract conf function to basically just extract the information that we want to have, which is the 50% and 95% confidence interval. And the way we do this is we, again, use the map command, because the output of this line of code, and you can kind of check this to kind of just run the first two lines here. The output of this is still a list, okay? And so we can still use map to apply a function to each element of that list that has been basically, that is the output of the first two lines of code here. And but one thing that we're doing slightly differently is we're using map_dfr. What map_dfr does is it, again, applies a function to each element of the original list, but then rather than as an output creating a new list, it creates a data frame, and this data frame will be basically each output from the original command will be added to the data frame by row. Okay, so we're basically running this extract conf command for each regression model that we computed for each individual sample. The output of that is as we saw previously, the output of this extract conf command is a 2x9 tibble, and by specifying map_dfr, we're ultimately kind of attaching all these 2x9 tibbles by row on top of each other, so that the resulting tibble is then, that is now CI_SAMP for the confidence intervals in these of these samples, is now a 200 by 10 tibble. Why 200 by 10? It's 2 for each regression model, because we had an intercept and a slope. It's 100 separate samples, so we have 100 intercepts and 100 slopes. And we have the 10 different variables that are corresponding to the output of this extract conf int function, as well as a sample ID function, which or a sample ID variable, which I specified here, which just helps us identify, okay, which of these samples did these coefficients ultimately belong to, right? So we're doing, with 3 lines of code, we're doing quite a lot of computation, right? We already we had a population, we took 100 samples from that population, we ran 100 regressions, and now extracted, for each of those regressions, essentially extracted 200 coefficients, one for the intercept, one for the slope, and 200 regression, or for each of those, 2 sets of confidence intervals, the lower bound and the upper bound of the 50% and 95% confidence interval. So that's quite a lot of stuff that we managed to basically compute with very little code, actually. Okay. Make sure to kind of go through that step by step and kind of try to follow the logic of the map command and so on, and make sure to go back to some of the other video content on the tidyverse package, as well as the R for Data Science book, if you want to have a little bit more information about how to use map and how to kind of replace traditional loops in R with by mapping functions over lists of elements, the way I showed it here. Okay. Um, now we can, as the last step, we can plot the coverage of the confidence intervals. Okay, and so what we're going to do here is we take our CI underscore SAMP, which is now the data frame that contains all the confidence intervals, both for 50% and 95% levels. And what we're going to do is we will just, since we're only focused on the slope itself, we will just focus on observations for our x variable. We don't want to include the intercept, and then we'll create a little ggplot with two or three aesthetic mappings. One on the x-axis we have the sample ID. Right here on the y-axis we have our estimate, and we will specify a color mapping dependent on whether the 50% confidence interval includes the true value, which, if you remember from our simulated population, is equal to 3. So we will have two different colors of these confidence intervals depending on whether the 50% confidence interval includes the true value or does not include the true value. We'll add a horizontal line for the true value, which is equal to 3. We'll add, of course, points for each point estimate, and we'll add line ranges for both confidence intervals, both for the 95% confidence interval and the 50% confidence interval of different widths, so we can distinguish them. Okay, and so that's a lot of ggplot code, but the result is quite nice. It looks exactly like this. We have on our y-axis our estimate and 50 and 95% confidence intervals. We have each sample kind of in a row on our x-axis, and we see the thicker confidence bound is the 50% confidence interval, and the more narrow one is the 95% confidence interval. And now if you look at the specific example, approximately 50% of those 50% confidence interval actually include, if you look at the red and blue confidence intervals and point estimates, you'll see that 50% of the or turquoise, and you'll see that around half include the confidence or around half of the confidence intervals include the true value. 3 and half do not. For the 95% confidence interval, of course, the coverage is 95%. So approximately 95% of the larger confidence interval include the true value. Okay, so one thing that is important to kind of keep in mind and to repeat again and again is that this confidence interval does not imply that if you have a given confidence interval that you have a 95% chance that the true value is in that confidence interval or not, right? So suppose, for example, in our sample that we collected, we only have one sample, and we had this specific estimate with this specific confidence interval. We can't say that we have a 95% chance that the confidence interval includes the true value, right? Because the true value is either in the confidence interval or it's not. We don't really know the probability of it being in it or not. The only thing we can say is that if we repeated the data generating process, if we repeated the sampling procedure, then 95% of our confidence intervals that are computed in this way would include the true value. Okay, and this is kind of what is visualized in this specific plot. Okay. All right, and next, in the last video, I'm going to talk a little bit more about simulation.